Welcome to our 39 lecture in combinatorics. Today we'll talk about planar graphs, and we'll start by a motivating example. Say we have three possible utilities, water, gas, and electric, and you have three houses. Let's call them H1, H2, H3. And what we'd like is to connect these houses to utilities such that the connections do not cross. So we assume that this is done by cables or pipes or something like that. And so if we look at house one, we can connect it to each of the utilities by these segments or curves. So we have no problems. Then if we go at if we try house two, then we can connect it to electricity like this. And if we want to connect it to gas, we can go around this way. Similarly, you can go around on the other side to connect it to water. And now we're left with the last one with house three, and we like to connect this one to the other ones. And we can connect it to gas this way, and we can connect it to water. But it seems like this electricity and the house three, if we try to connect them by any curve, you're going to end up crossing this one of the golden connections. So you can try to do here, but you run into trouble there, for example. So it seems like this is not this is not possible, and that's indeed the case. And so what this problem deals with is having a graph, in this case the complete bipartite graph K33, and trying to embed it in the plane with the vertices being drawn as points and edges as simple curves connecting the points, such that no two edges intersect except or no two curves intersect except at their endpoints. So if that's possible, then that graph is called planar. So let's give some definitions, some formal definitions here. So first, a curve for us will be just the image of a continuous function say from some closed interval, say 0, 1 to r squared. Okay, so you have some points in the plane, and let's say this is f0, and then you have some kind of continuous curve that changes up to f1, or you could have another situation where you have here f0, and it goes like this, coils, and this is f1, something like that. Now, if the curve doesn't intersect except possibly at the endpoint, so if all these points on the curve are different except for possibly f0 and f1, then that curve is called simple. So this one here on the left is simple, and the one on the right is not simple. Not a simple curve. So I can give now the definition of a planar graph. So a graph gamma planar if it's vertices and edges. Vertices can be represented as points in the Euclidean plane, and its edges can be represented as simple curves between their endpoints. Such that for any two edges, their corresponding curves can only intersect at their endpoints. We can say it this way: do not intersect except possibly at their endpoints. So that's when a graph is called planar, if we can embed it in the plane with these properties. And such embedding, if it exists, it's called plane embedding or drawing of gamma. Okay. So that's what the planar graph is. Sometimes this plane embedding, plane drawing is also called a plane graph. So let's see some examples. So let's say we have the graph, let's say we have the complete bipartite graph K23. This is clearly the drawing that I draw there is not a plane drawing. But just because it's not a plane drawing, it doesn't mean that the graph is not planar. You can draw the graph in a different way. And another way to draw it is this way. And this is the same graph K23, but this is a plane drawing or embedding. And that implies that K23 is planar. Okay. Now note that there could be several plane embeddings for a given graph. So if we take, for example, this graph here, gamma, this is one plane embedding of it, which is different from if we draw the graph this way. Okay, and so the same, so that's a simple observation, a planar graph may have different plane embeddings. And different, we haven't said what different is, but just from the picture, they seem that these things are different. Now, when we have, let's say we have one of these planar embeddings, something like this. Let's say we have this graph here. Call this also gamma. See the vertices and the edges, they split the plane into some regions, and these are called faces. So first I want to define what a region is. A region in the plane is an open set, let's call it W, such that any X and Y distinct points in the set really contains a curve from X to W to Y. Okay. Now we'll only focus on connected graphs here. So all the graphs that we'll deal with are connected. So if we have a connected plane graph, so a drawing of a planar graph in the plane, so given connected plane graph gamma, we can define a notion of a phase. A phase of gamma is a maximal region in the plane that doesn't contain any points. Any points of gamma, any vertices of gamma. So in this situation that we have here, the graph in this picture, we have what, 8 vertices, and we have we have I think 8 edges. So maybe let's draw a bit more edges. Okay, so this is our graph here, and it's a plane graph. Now, what are the faces here? So I will draw the faces, and I will represent them. And so first face would be here, and I will write the number of edges in that face. This is 3. This triangle. So let me give the vertices some names. So let's say 1. Well, let's call them letters A, B, C, D, E, F, G. So we have these vertices, and the first triangle with the purple, where I put the purple tree, the first face is a face that is bounded by this, it's the interior of this triangle with vertices A, D, and G. And similarly, we have a face of with 4 edges on its boundary, bounded by B, C, D, and A. B, C, D, and E gives us another face there. We have another face here of a triangle between D, G, and E. And now what we have a face on the outside, which is an outer face. And for that face, so for a face, we can define the length of a face. So the length of a face, it's not a farce, length of a face is the number of edges in the closed walk around its boundary, around the boundary of the face. So far for the graph that we have in our picture there, we have 4 faces, 2 of length 3 and 2 of length 4. And now we are going to do a walk. So let's say we start at A and we walk around the face. So I walk here, I get 1 edge. Then I walk here, I get the second edge, third edge. Now I come up around it. So I count that edge twice. So I have 4 edges, 5 edges, and now 6 edges. So this outer face, this is called the outer face, which is unbounded, and it has length 6 in our case. Okay. Now, so I hope that makes it clear. Let me give you one other terminology. It's about the dual of a planar graph. So let's say we have the same graph. A, B, C, E, F, and G. And we can define the dual of a graph where for each face we create a vertex. So each face we create a vertex. So let's put the vertex for the outer face here. Well, let me do it in blue. This one is here. And the other vertices, we have 4 other faces, so I can put there those, represent them on as these purple dots. And now for each, whenever you have whenever you have an edge which separates two faces, not necessarily distinct, you put an edge between those faces. So clearly we have an edge here because we have this edge between B and E. We have, these are clear here, these edges. And here we have two edges actually that separate, so it's both. So this dual, you see, it's a multigraph. Now we have another edge here, BA, another edge here, HG, and then we have a loop because the edge EF, you know, it's kind of separates the outer face, so you get this multigraph. And you see that the multigraph that we get, the dual graph, this is called the dual graph, and it's denoted by gamma star. The dual graph, maybe I'll draw it in this dual graph. We gave a definition by an example. This is also a planar graph. And so if we have for our original graph, gamma, we have V vertices, E edges, and F faces. Now for gamma star, dual, the vertices and faces, well, so you have a switch. The number of vertices here will be F, so F is a number of vertices. The number of edges is actually the same because the edges stay the same. And then, yeah. And we can try to figure out how many faces you have here for the dual graph. Now it's clear that, well, maybe not so clear, but if you think for a little bit, and if you take the dual of the dual, you get the graph back to itself. So the dual of the graph is the graph itself. So now, okay, so what we want to do is, so let's look a little bit at let's deal with the faces. So let's take a couple of more examples. Well, can do a calculation here. So for the graph that we have for gamma, the number of vertices is what? So A, B, C. I think we have 7 vertices. We have the number of faces is 5, and the number of edges is, we have 2 cycles there. I think it's 10. Yeah. And for the dual here, so we have gamma star. So gamma star has 5 vertices. It has the same number of edges, 10 edges. And we'll have also 7 faces. Now, here's some more examples. So let's do one that is drawn in different ways. Let's say we have one planar embedding. And we have embedding, but of the same graph. These two graphs, hopefully it's not too hard to see that they're the same. And so what can we say about their parameters? So in each case, the number of vertices is the same. So So the number of vertices is 7. The number of edges is the same because the graphs are the same. So it's 8. And it turns out the number of faces are the same. So there are actually 3 faces. So if we denote, let's say for j greater or equal to 1, let's call fj the number of faces, j edges. So on the one on the left, what do we have? We have this triangle. So I'll do the same thing as before. I'll write the number of edges inside it. So that's 3. Now for this, the second bounded face here, we walk, I have 1 edge, 2 edge, 3 edge, 4, 5, 6. So that's 6. And for the one on the infinite, the outer face, I have 1, 2, 3, 4, 5, 6, 7. So I have 7. So in this situation, we have that we have f3 is 1, f6 is 1, and f7 is 1, the outer face. Now over here we have another one of length 3, the triangle, and then if we do the other bounded face, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this one is 9. And the outer face, it's clear that it has length 4. So in this situation, we have f3 equals 1, f9 equals 1, and f4 equals 1. So the number of faces of each length are different, but the total number of faces is the same for both. And it actually, once you have the number of vertices and the number of the edges, the number of faces is determined. We'll prove that in a second. Before we do that, let me just quickly give you one proposition here. Namely that in any plane graph, if you sum up, the first one is obvious, if you sum up j greater or equal to 1 fj, we get a total number of faces, say part A. And part B, if you sum up for all j greater or equal to 1, j times f of j. So for each face of its length j, we add up the number of edges in that face. So essentially here, we're counting pairs of the form edge face for that edge E being contained in that face F. So E is contained in the face F. And so that's the number, but you can count it the other way around. Each edge is on the boundary of 2 faces, could be not necessarily distinct. So by that double counting, this equals twice the number of edges. So you can check this result on these examples. So again, even if the phase vectors are different, you still have this equation. Now, let's move now to Euler's theorem. So Euler's theorem, it's not quite precise. Euler proved many theorems. So I say the theorem of Euler says that in any connected plane graph gamma with v vertices, e edges, and f faces, we have that v minus e plus f equals 2. Now, there are different ways you want to remember this. Perhaps the easiest one to remember is that you can rewrite it as e as being v minus 1 plus f minus 1. And this is the number of edges in a spanning tree. of gamma, and this is the number of edges in a spanning tree of gamma star. I'll come back to this in a little bit, but that's one way that you can remember it. Now, if you go on Google David Epstein, he's a professor of computer science at UC Irvine. So he has compiled a web page on which there are, last time I checked, 17 proofs of this theorem. So the one its interpretation is of this form. I think it's, I agree with him, it's the most intuitive and natural. But we'll give first we'll give a different proof here. We'll give a proof by induction, and you can do induction on whatever. You can do induction on vertices, number of vertices, induction on number of edges, and so on. So induction number of faces. So let's do induction on V. So on the number of vertices, if V is 1, again, here for plane graphs, they could actually plane multigraphs. So if V is 1, then the graph consists essentially of a bunch of loops, okay? And you can draw them in different ways. But what is happening here? So if you could have the graph just being one single vertex, in which case E is 0, V is 1, and F is 1, and you know, V minus E plus F equals 2, so that's true. And now, if whenever we add a loop, what happens? The number of edges goes up by 1, the number of vertices stays the same, and the number of faces goes up by 1, becomes 2, okay? So the contribution between E and F in this formula, it cancels each other, so you have V minus E plus F equals 2. So again, if you add another loop, you get E is 2, V stays the same, number of faces goes up, and so on. So the formula is true for if you have this bouquet of loops. And now for the induction step, we can take a graph and let gamma be a plane graph. V greater or equal to 2 vertices connected. Okay. And what we do is, let's say we have this graph, something like this. And then you take an edge. Let's say we have an edge in the graph. E is a bad name for it because we already have E, but so let's call it E0. If you have an edge in gamma, you contract gamma, so 0, it's a graph obtained by contracting E0. So in our situation, the graph, so if these are the endpoints X and Y here, they become one vertex. So you have here the vertex that stays for both X and Y. So you can think of X and Y kind of getting closer to, you know, contracting into one single vertex. So this is, let's say, gamma prime. Now, when we contract, so this is gamma prime, which is, yeah, gamma, where you contract E0. So in gamma prime, what's the number of vertices? Well, this is V prime, which is V minus 1, because X and Y, we had 2 vertices before, and now we have just 1. Now, we contracted, and the number, what happened to the number of edges? Well, the only edge that disappeared is the edge E0. So E prime is E minus 1. And what about the number of faces? The number of faces stays the same. As you see, the one that had cardinality 5 here became one of cardinality size 4, but everything else stays the same. So f prime is the same as f. But now, by induction hypothesis, on gamma prime, we have that v prime minus v prime plus f prime equals 2, which gives us, if we replace those numbers, v minus 1 minus e minus 1 plus f equals 2, which tells us that v minus e plus f is 2. So you can see that you can give a similar proof if by induction on the number of faces or a number of edges. You pick an edge and you delete it. If you disconnect the graph, so first you can start with a tree. If the graph is a tree, then Euler formula is satisfied. Otherwise, if the graph is not a tree, you have at least one cycle, so you have at least one edge whose deletion doesn't disconnect the graph. Use that edge, and so you delete that edge, and you have a graph that has fewer number of edges and actually fewer number of faces. And then you can use induction to prove the result. Like I said, the more intuitive proof is the one that involving the dual. So the one that you can think in terms of this equation here, E equals v minus 1 plus f minus 1. Let me maybe give a hint of it here. So let's say if you have a graph, say something simple like this. Okay, so this graph has v equals 5, number of edges equals 6, and number of faces equals 3. So you can construct the dual. So you can construct the dual graph. So let's say this vertex here, here, and here. This. Okay. And then what you can do is you can take a spanning tree in our graph. Let's say this one. And from that blue edges, you get v minus 1 edges. You see those, yeah, you have v minus 1 edges, these blue ones. And then the remaining ones, like if you look at the other ones that are here, the other edges that are here, they correspond to these edges in the dual, and they form a spanning tree. So the red one is a spanning tree in gamma star, and the blue edges are a spanning tree in gamma. And the total number of edges in the graph, which is E, actually it splits between the edges in the spanning tree in blue, so that's v minus 1, plus the number of edges in the spanning tree of the dual, which is f minus 1. That's the gist of that proof. Now, Euler theorem has several consequences. So one corollary is that the number of edges in a planar graph cannot be too large, and one can prove the following. So one, if gamma is again connected plane graph. So yeah, by the way, if the graph is not connected, then Euler's formula, it doesn't work. So you need connected, like this formula. Connected plane graph, then the number of edges is at most 3v minus 6. And you can have improvements. For example, if gamma is connected and no triangles, and E is at most 2v minus 4. And there is a formula if you have the general one is gamma connected with a certain girth, then you can have there's an upper bound on the number of vertices, so connected girth G. So this is the length of a shortest cycle. Then you get the number of edges is at most G divided by G minus 2 times V minus 2. So let's say G greater than 2. Okay. So the proof is the same for all. It uses this equation that summation of J greater or equal to 1 J times F of J is twice the number of edges. Okay. So in our situation, let's say we're looking at connected plane graphs with girth greater than 3, so we don't have multiple edges or loops. So each phase, so we have this sum of J, 1 J, J, Fj equals 2 times number of edges, and we have that each Fj is greater or equal to 3, and F1, F2, no, Fj. So say F1, F2 is 0. So we have 2e is a summation of J greater or equal to 3, J times Fj, which is greater or equal than the summation of J greater or equal to 3 times Fj. You take 3 as a common factor and it's 3 times the number of faces. So 2e is greater or equal than 3 times the number of faces. And now you have Euler formula V over here. And you can just replace the number of faces, which is E minus V plus 2. You plug it into here, and we get 2E greater or equal than 3 times E minus V plus 2. And when you unpack it, you end up with E at most 3 times V minus 2, which is 3V minus 6. And now the proofs for 2 and 3 are similar. And the one for it just uses the fact that for 3, the most general one is that because you have girth G, means that F1 equals F2 equals Fg minus 1 equals 0. So then 2e, it's actually a summation over all J greater or equal to G of J Fj, and this is greater or equal than G times the summation overall GFJ, and this is the girth times the number of faces. And you do the same substitution here, and it gives E at most G times G minus 2 times V minus 2. Okay. So with this result, you can prove a whole bunch of things. So gamma plane graph. One corollary that's very useful is that the maximum degree, the minimum degree of gamma is at most 5. So that means there exists a vertex x in gamma such that the degree of x is at most 5. And you can prove other things like with K5 is not planar, complete graph, 5 vertices, K33 not planar, or Peterson graph not planar. Some other similar results. Actually, it's a general theorem, and this is a powerful theorem of Polish mathematician Kuratowski in the 1930s that states that a graph is not planar if and only if it has a subgraph that is a subdivision of K5 or K33. So this kind of topologically, K5 and K33 are the obstruction to being planar. So this is K5, and a subdivision of it, you take an edge and you can replace, you can add vertices on that edge. Okay, replace each edge by a path. The path could stay as the edge, but you can put many vertices if you want. So that's an example of a subdivision. And similarly for K33. Can have now, so let's prove the following theorem. So this is a theorem due to Hewitt from 1890 that every planar graph can be properly colored with 5 colors. Of course, there's a 4-color theorem, which was proved by Appel and Haken in 1978, where you replace Appel. That says that chi of gamma is at most 4. That's much harder, and we won't do anything like that here. So we'll just prove the 5-color theorem. So the proof of it is by induction on the number of vertices. So if the number of vertices V is at most 5, then it's clearly that chromatic number of that gamma is at most 5. So that's easy. So now for the induction step, assume that V is greater or equal to 6, and let X be a vertex in V gamma such that the degree of X is at most 5. So that's key. We have a vertex of small degree. So let's say we have a plain drawing of that graph. We have X, and let's say, well, we have, so we look at gamma prime, which is gamma minus X. Gamma prime is a planar graph. So by induction hypothesis, chromatic number of gamma prime is at most 5. So there is a proper coloring, proper 5 coloring of gamma prime. Okay. Now, if the degree of X is at most 4, this is the easy case, then take a proper 5 coloring of gamma prime. Now what happens is the vertex X can see at most 4 colors on its neighbors. So that means that there is a color available for X that doesn't conflict with that does not equal a color on its neighbors. And so therefore we can extend the coloring of gamma prime to gamma, and we get a proper 5 coloring for gamma. Now, the hardest case is that the degree of X is 5. Okay. Say we have something like this. So this is a vertex X, and we have its neighbors A, B, C, D, and let's call it G. Let's keep E and F. And now the hardest case is on every proper coloring of gamma prime. These vertices get different colors. So A gets red, B gets blue, C gets green, D gets gold, and G gets purple. Okay, so that's the hardest case. All right. So in this case, what do? We cannot we don't have a color available for X. So somehow we have to make a color available for X. So what we do is we look, for example, at the subgraph gamma induced by colors red and green. So this is the subgraph. So we take a proper 5 coloring so you take a proper 5 coloring of gamma minus x. We have a proper 5 coloring there. And we look at the subgraph induced by vertices with those colors. This and this. So A and C are in that graph. And if I look at the two possibilities, there's a possibility. So in that subgraph, the neighbors of A have to be colored by green, because this is a proper coloring. So if I have A has neighbors of that color, they have to be colored green. And if C has neighbors of that color, they would have to be colored red, and so on. Now you have two possibilities. The A and C are not on the same component in this graph. So in that case, so if A and C are on different components, then what we do in one of those components, we switch the red with the green. Oops, sorry. With the green. Like this one. So let's say it's like in the picture there, you cannot have this alternating path between them. So what we do is we color here by green now, and we color here by red. And what happened in this situation, the neighborhood of X has 4 colors, and we have a color red that we can put over there, and we are done. Okay, so that's when if A and C are in different components, then we can prove that the chromatic number of gamma is at most 5. Okay, now what if that doesn't happen? So what does that mean? So that's the case here. We're done. Well, in that case, it means that there is a path that alternates these colors, like the one that I draw here, that goes between A and C, and we cannot switch the colors. So in that case, what do we do? Well, we look. So if otherwise, if A and C on the same component, then we look at a similar graph, gamma, induced by what colors? Induced by the blue color and by the golden color. So where B and D are contained in that graph. Similarly, if B and D are in different components, we can switch the colors in one component. So okay, so that we can save a color. But what if they're not in the same? Is it possible for them to be in the same component? Well, that would mean that from A, I can do this alternating path, something like this. There, I have this. But here, I have that B is in the interior of this region, of this part of the graph. But this vertex with golden is on the outside. And there's no way for me to connect them without crossing an edge. So that means that these two vertices, these two vertices, one with color dark blue and one with color gold, they have to be in different components, and therefore I can switch their colors. And in that situation, if I switch their colors, I can replace this one by blue, replace this one by gold, and so on, and still be a proper coloring. And what we do, that saves me a color to put on X, which is gold, and gives me a proper color. So that's basically you end up with a way to extend the 5 coloring in this case as well.